Good morning, guys. If you can give me some green checks, please. I have a feeling there will be a few people showing up momentarily. Looks like we're a bit light on participants today. I wanted to start with any questions you might have from the earthquake activity that we looked at the end of class last day. Was there anything that came up when you guys were going through that was problematic, difficult, didn't understand, need clarification on? Or was everything in the earthquake activity pretty self-explanatory and straightforward? Hoping self-explanatory and straightforward. See anybody feverishly typing questions, so I have a feeling you guys all did a okay job on it, or haven't even looked at it yet. Could go either way. Always uncertain. All right, today what we're going to do is I think there's one page left in your learning guide on volcanoes that we need to talk about. We'll look at a couple little video clips and we'll talk about a couple volcanic eruptions. And that's really it. I hope you guys can submit your Unit 10 learning guide either today or tomorrow. And don't submit it tomorrow at like 3 o'clock because it's not going to get marked till after the break, which means that you won't have the test password, which means that you'll be done the material and then you'll have to wait 2 weeks before you can actually write the test. So if you are going to finish Unit 10, make sure it's hopefully today. There's really probably no reason it couldn't be today. Or if you can get it in tomorrow morning before about noon, I can guarantee you the password out before the end of the day when I leave. In terms of just science, I mean, if you're behind, obviously getting caught up should be a priority for you. But for those of you who are caught up, I'm really happy with the progress you guys have been making. Grades are quite good if you have everything in. And I hope you guys can enjoy the break and you don't have to spend it doing science. So if you're caught up, as a reward, I think it's important that you guys take some time to relax over the break and take a break because it's a break. So if nobody has any questions about the activity, I'm just going to jump right into the few slides that I have left here on volcanoes. And we can just fill in that last page. I think it's page 13 of your learning guide, perhaps. Yeah, there'll be a password for the test, Jenna. The reason the tests have passwords, you guys seem to sometimes be confused on this, is that I don't want you to go through a whole learning guide doing everything wrong and then write the test and say, oh, I got everything wrong on the test. If only I would have known. That's kind of the idea behind me going through your learning guide to make sure everything looks good on it before you complete the test. Now for the first, 4 units, units 1, 2, 3, and 10, it's not a huge deal. Like the material's all just kind of pulled right out of the notes, and there's not a lot of, sort of problems that require sort of procedural things and things of that nature. So it's not a big deal. But when we get into Unit 4, which is chemistry, which will start after the break, it all of a sudden becomes really important that your learning guides are being done properly because there's some calculations involved, things like that. And if you're not doing your learning guide properly, it'll really affect your test mark. So it's just a good habit to get into. I do it with all my classes, and it's just kind of how we do things. So here you go. Volcanoes. We're going to talk about 2 types of volcanoes, and there are more than 2 types of volcanoes, and I think, well, I'm not sure. Sometimes, very rarely will you ever see a question on a test that requires you to know the types of volcanoes, but the 2 main ones, and then there's kind of subcategories from there. So these are composite volcanoes, and composite volcanoes usually occur at subduction zones. So anytime you have a convergent plate boundary, 2 plates coming together, one plate goes under the other. As it dives deeper below it, it starts to melt down at the bottom, and that magma rises up, kind of cracks through, and starts breaking through the surface and creating this volcano. And volcanoes will start really small and they'll get bigger and bigger and bigger. Each eruption adds a new layer of rock, it makes it a little bit taller. And composite volcanoes are very famous for not erupting nice and smooth. They kind of shoot out rocks, and they're full of gas, and they kind of explode, which is a problem, especially if you live near one of them. So the composite volcanoes are the type of volcanoes we have in our neck of the woods, and they are dangerous for people compared to the nice, beautiful volcanoes you see in like Hawaii, where you have this amazing lava flow. It's kind of like a river, and you just look at it and it kind of just goes down the sides of the mountain. It looks pretty amazing. You don't get that as much with these types of volcanoes just because of how they're formed. So this is our neck of the woods, and believe it or not, we live in a volcanically active, very seismic area. We don't really think of there being a lot of volcanoes near us, but there are. There are tons of volcanoes near us. So remember, off of our coast, we have this little plate, the Juan de Fuca plate down. You can kind of see it at the bottom here. And the Juan de Fuca plate is, it's being subducted under our Pacific plate. So the Pacific plate is where Vancouver Island and the rest lie. So right on the plate boundary where the subduction occurs, there's no volcanoes. These are just showing that this is subduction zone. But because this plate is diving, the Juan de Fuca plate, diving under this Pacific plate, when you go back off the edge of the Pacific plate a ways, that's where the magma starts to rise up. Now, in BC, we don't have nice, flowy magma volcanoes. We end up with these composite volcanoes, and these are the ones that just will explode eventually, which is a problem, because if you look at where Vancouver is down here, fortunately I can't get my cursor all the way down, but obviously Vancouver Lower Mainland just below here, this volcano Garibaldi is a dormant volcano, but it's still kind of considered able to erupt at any time. And if it does erupt, it could have sort of devastating consequences for the millions of people that live in Vancouver. All the other dots on this map show either lava flows or other volcanoes. So there are lots of seismically active areas in BC and lots of volcanically active. If you go to like Nakusp area, has anyone ever been to any of the hot springs in BC? The kind of close ones to us, you have Harrison Hot Springs, you've got Nakusp has hot springs, Harrison, Nakusp, there's a few other ones that I can't really think of right now. Anybody ever been to a hot spring in BC? Harrison and Cusp are the only two I can think of right now. It's kind of disappointing. Your dad has. Okay. So there's lots of places in BC where you can go, and there's hot springs. But why is the water hot? Well, the water's hot because, you know, where the water is under the ground, there's magma that kind of gets close to the surface. It heats the water up, the hot water rises, and you get nice warm pools of water. And they're all over BC because we are a volcanically sort of active region. But our volcanoes aren't the type of volcanoes you think about. So the picture behind my head here is Mount Garibaldi. It actually just looks like a regular mountain. It doesn't look particularly special like you would consider a volcano to look, but it is capable of erupting at any sort of time. The really interesting thing about volcanoes is they'll eventually, you know, become a little bit more seismically active. You'll see lots of small earthquakes, and then they'll kind of explode, especially around our area. You guys have likely all grown up or lived in Kelowna at some point in your lives. Does anybody know any of the volcanic sort of history around Kelowna? Does anyone? There's a few volcanoes close to Kelowna, very, very old ancient volcanoes. Anybody know? All right. So if we look at this side of this composite volcano here, you can see down in the middle under the Earth's crust, there's a magma chamber, and then usually kind of in the middle of the volcano, you'll get a big pressure buildup, and it'll kind of expand out, and it'll form something called a caldera. And a caldera is just basically kind of sounds like cauldron, but it's a big big sort of cavity in the middle of a volcano that kind of holds a bunch of magma as that pressure kind of builds. So if you are in Kelowna right now and you can look out a window and see a mountain near you, there's two calderas that have been left after kind of the glacial periods have scraped away all the rest of the volcanoes. So if you look to the east of Kelowna, Black Mountain is called Black Mountain because it's an old volcanic caldera. Why is the rock black where everywhere else the rock isn't black? Because it was magma. Mount Bushry, also a caldera of a volcano that existed thousands of years ago. So like I mentioned a few classes ago, or maybe last class, there's an old fault line that runs right down the middle of Okanagan Lake. You know, thousands of years ago, we lived in a fairly volcanically active area. So the remnants of those volcanoes, Mount Bushry and Black Mountain, are two ancient volcanoes that used to exist where we live. Mount St. Helens. Now, I'm going way back with this, but Mount St. Helens erupted in 1980, which is even before I was born. So you guys are like, you know, this is way, way before you were born. But Mount St. Helens is significant because it is kind of in the southern part of Washington State. And if you've ever driven down towards Vancouver on a clear day, you look south. Does anyone know the name of the mountain you can see from kind of Highway 1 as you go down towards Vancouver? You look south into Washington State. There's a couple of large mountains there. They're actually volcanoes. Anyone know the names of them? Mount Baker, you got it, Costin. So Mount Baker is just south of Vancouver. It's in Washington State. And there's also Mount Rainier, which is just a little bit further south again. And then in that same chain of volcanoes, you have Baker, Rainier, and then Mount St. Helens is down at the southern part of Washington State. These are all composite volcanoes, and composite volcanoes don't, you know, have nice smooth flows of magma. They build and pressure builds, and then they eventually explode. So this image at the top of the page here is an actual picture from a plane taken in 1980 of Mount St. Helens erupting. The picture to my left, my right, everything's backwards on the camera. My right here, this is a picture of the trees that were knocked down when the volcano exploded. So there was a shock wave produced that literally was like several nuclear bombs going off, and it literally knocked down trees. And the most amazing thing about this is if you look at some of these trees, they're kind of protected by, you know, a ridge, and the trees were kind of snapped off like halfway, some of them, just because that's where the shock wave hit. It's pretty incredible to think of the amount of energy. Yeah, Costin, the ash, we'll look at the wiki page here in a second, but the ash went, my parents lived in Kelowna in the 80s, and they said they couldn't see the sun for a few days in Kelowna in 1980 because there was so much ash in the sky. If you, well, you guys don't remember the Okanagan Mountain Park fire probably really clearly, but you couldn't see the sun. It was very similar to that. The ash covered, it went and covered at least 5 provinces in BC, or in Canada, so BC, Alberta, Saskatchewan, Manitoba, Ontario. That's how far the ash cloud went. Covered like 11 states. Pretty incredible. So it just so happened that there was a person standing on the side near the mountain. I should mention that 53 people died when Mount St. Helens erupted, so don't want to take this stuff too lightly, but here's a video of, it was a bunch of stills, and these stills have been put together with a little bit of computer trickery to kind of link them together to show what happened when the volcano erupted. So this was over a few like seconds. It happens kind of really slowly in the clip, but we're going to watch an ad first. Okay. Really good ad too. I wonder what it's for. Pixel. Thanks, Google. All right, so this is Mount St. Helens erupting, and when I say erupting, I guess I kind of use the term a little bit.
There is a certain fatalism amongst geologists who work around these volcanoes, as we all know that if you're going to work around one that's getting ready to erupt, there's some risk.
This is the guy.
Up in this ridge,
this is the guy now. You can see this is the north side of the volcano in the background.
Mount St. Helens.
So dude was camped out.
David had parked his trailer in front of the volcano's north flank to keep an eye on
and this was it before it
bulge.
erupted, so completely covered in snow and glaciers.
That same day, amateur photographer Keith Ronholm made his way to a scenic spot, also overlooking the volcano's north flank.
We're at Bear Meadow, where I was 28 years ago in 1980. I was 10 miles from the mountain. It seemed like a perfectly safe place to be.
Which are called lahars.
But just after 8:30 that morning,
so you can see that the volcano here it's still active. It's still erupting to this day. Here's the time lapse of it. So this is the largest landslide in recorded history. This is a mountain.
I glanced over at
a mountain that's several kilometers tall.
The entire north face was in motion, was sliding down. And it's such an unbelievable view that I like shook my head.
And the whole side of the mountain breaks off essentially, and you end up with an explosion. And you can see the landslide that occurred. So the trigger of this eruption was a magnitude 5.1 earthquake that just caused enough of sort of motion in the volcano for it to just literally break off on the side. You can't really get a good sense of the scale of all of the land coming off here. That's literally a whole mountain, just the side of it blowing off. So yeah, absolutely incredible how much energy was released. And the reason we bring it up is because all the volcanoes in our region are these composite type volcanoes. Mount Baker could erupt at any day. Mount Rainier could erupt any day. Mount Garibaldi could erupt any day. And they're not likely to erupt really gently. They're going to explode. Literally square kilometers of forest were knocked flat. Just crazy stuff. So I'm just going to actually go to Mount St. Helens eruption. Instead of the Mount St. Helens page. And I'm just going to scroll down to the bottom real quick. It gives you kind of idea of how much. This is a picture of the lake. This was taken in 2012. These are all these trees that are dead still floating around the lake because they basically got blown into the lake. Just crazy, crazy stuff when this thing went off. The ash cloud went several kilometers into the air. Here's a picture, as Costin mentioned, that the ash-covered British Columbia, obviously BC's not in the map here of the United States, but here's Mount St. Helens down in the bottom corner of Washington State, and everything in yellow was up to ½ an inch, so we're talking a centimeter of ash covered all of these places. And then obviously the cloud would look similar up and towards Canada. So yep, we definitely couldn't see the sun for a few days in Kelowna. Houses were destroyed, bad things happened. So these are the most amazing things. Before the eruption, the mountain was 2,950 meters tall. So that's taller than like Big White, if anybody wants to think of Big White. After the eruption, it was 2,549 meters tall. So 400 meters. Imagine 400 meters of anything just going straight up into the air. So imagine 100 meters going straight up into the air, and 400, like 4 times that. That much mountain just fell off and exploded out the side and just turned to ash like instantly. Absolutely incredible. Wouldn't that destroy crops? Yeah, a few days of blocking the sunlight out wouldn't be a huge deal, but if you had prolonged, blocking of the sunlight, then that could happen. And there's evidence to support that periods of high volcanic activity on Earth can lead to ice ages. So if you have enough big volcanoes erupting at the same time, it can block out the sun that reaches the surface, and you can actually enter an ice age because You get, you know, all it takes is kind of like one summer where the snow doesn't melt, and then boom, the next year you get snow on top of that snow, and it can trigger ice ages and things like that. So pretty incredible. It was a 5.1 earthquake that started it. The landslides were hugely devastating because you had all those glaciers, all that snow. They melted instantly, and it caused something, mud and glacial debris just turned to liquid and slid down the mountain, and they're called lahars. There was a pyroclastic flow. You know, the lateral blast was traveling at 483 kilometers an hour. That's fast. I don't think I could run that fast. It covered 596 square kilometers, just like, you know, absolutely incredible numbers. The temperature of the blast was 349 degrees Celsius. So that's hot enough to basically incinerate everything in its way. Just the numbers are just incredible. Like 9 million meters cubed of timber was knocked down. 9 million cubic meters. Not even 9 million. Like, you could have built 300,000 houses with the amount of trees that were knocked down. 300,000 houses. There aren't even close to 300,000 houses in Kelowna. Like, it's just like absolutely crazy. Lahars, so these are the mudslides. They were, you know, traveling at 40, 50 kilometers an hour. The eruption column, so the cloud that was created when it erupted reached 24 kilometers high in 15 minutes. It just kind of like, the pyroclastic flow is kind of like the hot gas that's created when a volcano erupts that slides down the side of a mountain. And these were traveling at 130 kilometers an hour, and the temperature was 1300 or 700 degrees Celsius. So you imagine a gas cloud moving faster than your car can drive, and the temperature is 700 degrees Celsius in it. Like, it's just, you know, absolutely just incredible to think of what happened in literally like less than a minute. Boom, this like 300 kilometer an hour blast. You got 130 kilometer an hour gas cloud that's 700 degrees Celsius. So Costin, when you say, it would be fun to be there, if you were there, anywhere close, you would have been dead. And 50 people did die, 50 to 60, depending on if you count people that were there directly, and then some people died like doing, you know, you have this big ash cloud driving towards you and you're trying to drive away from it, and then you crash your car and die. Well, did the volcano kill you? Kinda, not directly. The second type of volcano that we need to know of the kind of the three big ones is a shield volcano, and shield volcanoes happen in places that have hot spots. So we're talking Hawaii, there's some other places on Earth that have these hot spots. And the magma is very, very fluid. It flows out nice and smooth. You can see all the black lines down the side of the mountain here. So these are all just lava flows making their way to the ocean. Very non-explosive eruptions. The lava just kind of flows up over the edge and just kind of rolls down the side of the hill. These volcanoes don't get really steep because that lava just flows out nicely. They're not explosive. They're not really necessarily associated with any earthquake activity because they're in the middle of a plate generally. And I mean, volcanoes can erupt and be kind of explosive, but they're not like we would see with a Mount St. Helens type eruption. And Mount St. Helens could do that again today if it wanted. Like, there's still stuff happening in the volcano. The last type is the rift eruption. We've talked about these. When you have two plates moving apart, that's because magma is pushing up between them, and you get a long line of volcanoes. So this is in Africa. This is the East Africa Rift. And you can see that as the plate, you can clearly see the plate separating with these kind of whitish lines. As the plate separates, you get magma filling up the middle, and you get these volcanoes in a thick line all the way along the Rift Valley. So they aren't explosive, but they release massive amounts of magma. They're different than the previous shield volcanoes, because those shield volcanoes is just a small hole, small in like Earth size, relatively speaking, a small hole that lets magma come through. If you have a long ridge and those two plates are moving apart, that whole middle section just fills with magma. It doesn't, it's not just obvious magma coming through, but it can be in some spots. So we're talking East Africa Rift Valley, Mid-Atlantic Ridge, right off our coast, the Juan de Fuca Plate. On the westernmost edge of the Juan de Fuca Plate, you'll have a big rift volcanoes like this, but underwater. So those are the types of volcanoes that you should know. There's kind of 3 there. There can be subcategories beyond those 3. So that's it for the learning guide for Unit 10. Did anyone have any questions about the learning guide Unit 10 that you wanted to go through before I said see you later? Anything you didn't really know, understand, get? Anything from the, not the volcano activity, the earthquake activity that was kind of built into the course? The SP lag time, finding the magnitude of the earthquake, measuring the height of the seismograph spikes, and then using a chart to compare the height to how much it is on the Richter scale. Distances, anything in that regard? All right, we have 2 options at this point. Option number 1 is I say see you later, have a great break, get your Unit 10 learning guide in today, and I'll have the password out to you today or tomorrow, depending on when you get it in. Option number 2 is I give you a little bit of time to work on the learning guide, and you come back with questions you might have. So it doesn't much matter to me either way, but I'll take a vote. So option 1, sayonara, I got things under control, Mr. B, no worries. Option number 2 is, hey, let's take a little bit of time to look at this learning guide, and we'll meet back in, say, 30 minutes, and I can ask some questions then if I have any. So all I need is a 1 or a 2 in chat, and if a few people pick 2, then we'll just do that because it doesn't really much matter to me. But if everyone, there's a bunch of 2s. And if you don't vote, you can't complain about the outcome, remember? Leads, gotta quit being so difficult all the time. What's option 3, Leads? Would you like to suggest another option? Ooh, this is getting close. Cookie party. Are you bringing the cookies, Leads? Because I love cookies. All right, Leads is going to bake everyone some cookies in the next 30 minutes. And she's going to drive them down to the office here, and you guys can all come in. Just kidding, Leads. You don't have to bake cookies for everyone. All right, it looks like some people want to come back after 30 minutes and just, answer, have any questions. Yeah, for sure. So, Kylo, that's fair. If you think you have things under control and you don't want to sign back in 30 minutes, that's fine. I respect that. If you do have questions, I'll tell you what. Mr. Ross has queued up a timer for 30 minutes, but I'm going to just kibosh that completely. I'm going to say this. I'm going to go into my office, and I'm going to log into Blackboard, and I will be available until 11:30. And if you have questions, you can ask, and I can go through them. So we'll just cut the broadcast now. There's no point in me coming back. But I will go into my Blackboard in my office and for sure come back in 30 minutes. I'll put up a timer for 30 minutes. Costin, you can type your question right now and I can answer it. So I'll put up a timer for 30 minutes in Blackboard here. I'll come back, but if you do have any questions along the way, then just fire them into chat and I'll answer them on my computer. So I'm just throwing up 30-minute timer there. Question right now, page 4, number 2. My pages might be different, so Costin, if this looks different than yours, let me know. Page 4, number 2. Identify, discuss the 4 lines of evidence that Wagner to propose the continental drift theory. Is this the one you're talking about here? Is that the same question? Okay. So if we go back to the notes right at the beginning of Unit 10, we talked about Wagner and his ideas. And Wagner was the guy who came up with the idea for continental drift. But he didn't know how the plates moved. That wasn't until Hess came along later. So this is Wegener. He had these crazy ideas. So the 4 points are here, but we'll just look at them as images. The first piece of evidence he used was that the continents kind of look like they fit together like puzzle pieces. Africa really looks like it fit together with North America and South America. So that was his first piece of evidence. Second piece of evidence was matching geological features. So these are mountain ranges that run through the east coast of Canada that also match mountain ranges in the United Kingdom and into kind of Scandinavia here. So matching geological features was number 2. He also looked at fossil evidence of land-type dinosaurs that existed on different continents, and if those continents were separated by an ocean, it would be nearly impossible for them to develop at the same rate on 2 different places, completely independent of each other. So the continents probably were touching because these dinosaurs existed across multiple continents separated by large oceans in current day. And there's kind of fossils in Antarctica. The last is paleoglaciation. So the places like Africa and India, which are extremely hot now. India is like right on the equator. Australia, southern Australia. These are very, very hot places. They show signs of glaciers once existing. So that means that all of the continents, Pangaea, all had to be a little bit further south towards the South Pole at one point. So the South Pole, the geographic South Pole, actually used to be at the southern tip of Africa during this Pangaea period. So those were Wegener's 4 pieces of evidence: matching geological features, puzzle pieces, the paleoglaciation, and did I say fossils? Fossils, geological features, puzzle pieces, paleoglaciation. Those are the big ones. There you go, Costin. No worries. Did anybody else have any other questions before we sign off the live feed? And I'll stay in Blackboard. I'm just going to go fire it up in my office. And I'll be there until 11:30. Just come in. You can stay in, ask questions all the way through. All right. I don't see anybody typing. So if I don't see you, I hope you guys have a great break. I hope you guys have a chance to relax and take a little bit of a breather from school, especially those of you who are completely caught up. If you're not caught up, I look forward to receiving work throughout the break. The likelihood of me marking things over the break is extremely low. Just like you need a break, I need a break. So I'm going to spend time with my family, and I would like to relax and take a break from school, as I hope you do as well. So if you do submit something over the break, don't expect a reply right away. But that's not to say it's not important that you still submit stuff and get caught up. The last thing I will leave you with, I know I just keep talking, but the last thing I will leave you with is this. If you are behind now and you carry your behindness into April, so after the break, there's almost no chance of you making it through the course. And I say that as like a teacher who's taught Science 10 many times. The chemistry unit is kind of the first sort of difficult thing we do in Science 10. It gets a little bit trickier. Not to say it's impossible. People do very well. I've had students get 100% on the Science 10 provincial exam before, but it requires a little bit more process sort of stuff. So if you are behind, it is so important that you get caught up, because you don't want to be behind into the chemistry unit. Because if you're behind in chemistry already, you're just going to really struggle. It's going to come fast and it's going to be difficult. So it's super important that you get caught up if you are behind. I know most of you who attend class are always caught up anyways, but I just wanted to say that. So try to get as much work as you can done over the break. If you run into problems and whatnot, we can deal with it, but it's important to stay on top of this stuff, because once we start chemistry and then into the physics unit, things move fast and there's a lot of information there. So if I don't see you, have a great break. I'll see you after in April. If you do have questions, I'll be in Blackboard until 11:30 and happy to answer anything you might have. So thanks guys, talk to you soon.